This lesson is about Newton's method. It's a basic methods for finding roots of differentiable functions. Starting off with here, we're interested in the blue curve we see here at the top of the slide. And the blue curve is coming along. We see here at the beginning it starts below 0, and then it increases until it's above 0. With Newton's method, we first find some sort of an approximating value, and in this particular example, it's not too good of one. We pick it right here, which looks to be about 1.5 as our approximate root. And again, we just by inspection we could do better, but this makes a better illustrates the picture. So we approximate our curve at the point of our initial estimate by a tangent line. Okay, and so the idea is we then for lines we can find roots rather easily. We follow this on down, and the root, the approximation of our root is about here. In terms of our of the algebra of this, we solve the equation y is equal to f of x naught plus f prime of x naught times x minus x naught, which is the equation of our tangent line. We set it equal to 0 and solve. Okay, and in doing so, we find that this value x down here, where it's equal to 0, is where our line crosses. We would have x is equal to x naught minus f of x naught over f prime of x. Okay, and so the idea is that's a better approximation, and so we iterate this. So xn plus 1 is equal to xn minus f of xn over f prime of xn. And so we have to have a function that we can take derivatives of. Okay. So when we put this into Newton's algorithm, okay, the first idea is I'll call it the naive method, where we input x, our initial guess, and m, the number of times we want to run through the loop. And initially, our y value is going to be f of x, our function evaluated at that. And we go through our loop m times, wherein we'll replace x by x minus y over f prime of x. And then each time fy will become f of the new x, and we keep on doing this, okay, for m times. And when we get to the end, our answer is the value x. Okay. Now, and this is good. This will give us good, precise answers for most functions, but we can improve it and making it quicker. The idea is we input our initial value and the maximum number of times, and then we put in a couple of error tolerances. The delta is the error tolerance on our x, and the epsilon is the error tolerance on our y. And so we go through the same steps, replacing each number or each x with its successor, computed through this highlighted formula. Okay, but after we do that approximation, we do a test, and if the new approximation is within delta of the old approximation, we stop. Or if our y value gets to be, which is our f of x, f of our approximation, if it gets to be too small, we stop. Okay, And so in this case, when we get close enough, we don't just keep grinding away and wasting time. We stop it and go on to the other things we need to do. And this is how it can be implemented in say, a Jupyter notebooks. We have Newton's algorithm, and I will put my output to a list. And so here I define my functions in the code. I call f, and this is using our what's called the lambda functionality of Python. F is lambda. It takes x to exp of x minus 2, and so the derivative of this is just exp x to exp of x. And so then we go through this and we break. Well, for this particular one, I say we're going to start at 1. We'll go through it most 100 times. We'll stop if our successive approximations are within 10 to the negative 10th of each other, and we'll stop if our f of an approximation is less than 10 to the negative 10. And so when we do it this way, we stop on the third iteration, or I guess, the 0, 1, 2, 3, the third or fourth iteration, however you want to count it. And this is, we stop it because our f of our approximation becomes too small. On the next one, we replace our tolerances by 10 to the negative 16th. And here, after n equals 4, it's actually showing that, according to round off our approximation, it's dead on 0. Okay, so this is quick and this is good. And so let's look at the error. Okay, this is something nice, and I'll go through it here, but it's worth your time to examine the slide in the quiet of your own study. We have our error is our nth approximation minus what the actual value of the root is. So I mean, f of r is equal to 0. And so this is where we're using Newton's value, x sub n plus 1 is equal x sub n minus f of x sub n over f prime of x sub n. Okay, so, and we make the assumption that f prime of r isn't equal to 0 because clearly Newton's method is undefined if it is. Okay, we have to find some other method for functions where this happens. Okay, so on one hand, we can go through and say, okay, by definition, my n plus first error is here. So I replace my n plus 1, x sub n plus 1 by its Newton method formula. Okay, and then I rearrange some stuff. Okay, so I take my my r next to my x sub n, this leaves over my f of xn over f prime of xn. My xn minus r, that's just e sub n. So I rearrange that and I get it over a common denominator. Okay, and so there I have a expression for e sub n plus 1. Now, on the other hand, I can say f of r is equal to f of xn plus f prime of xn. Again, this is just using Taylor's theorem. Like I said, Taylor's theorem is very useful for these sorts of theoretical things. and f of r is 0 because r is our root, okay? So I have 0 is equal to f of xn minus f prime of xn times en. Again, just making direct substitutions, 1/2 en squared. Do some rearrangement on this, okay? And so I get that f prime xn minus en times en minus f of xn is equal to 1/2 of en squared times f double prime of ski. Okay, so we can divide the left-hand side of this by f prime of xn. Okay, and this will then reduce, giving us that en minus f of xn over f prime of xn. Okay, and substitute in en xn, okay, minus r. Okay, and so thus rearranging it, we have it all is equal to en plus 1. And so doing my substitutions, okay, and let's just show where the substitution, back into 5 there, I believe. Gets me that my e sub n plus 1 is 1/2 f double prime of r over f prime of r times en squared. And so we can now take a limit, okay, that as n approaches infinity, xn plus 1 minus r over xn plus 1 minus r squared. We run it through with all these substitutions, and we get it to be equal to c, which is greater than 0. So this will be quadratic convergence. Okay. So quadratic convergence is fast. All right, so the theorem on Newton's method we summarize. So let f double prime be continuous, and let r be a simple 0 of f. So that means that f of r is 0, but none of its derivatives are 0 on r. Then there is a neighborhood r, a neighborhood of r in a constant c, such that xn is in that neighborhood, such that if x sub 0 is in that neighborhood, we have that x sub n minus r is less than c times x sub n minus r squared for n big enough. Okay, and see, the idea here is that this, when we get this xn minus r to be less than 1, say, when you square it, it's even more less than 1, so it just gets smaller and smaller and smaller really quick. Okay. And so if we're lucky enough to have a second derivative function that is increasing, that it's convex, that means it's smiley. Okay, if it has a 0, then Newton's method will converge from any starting point.